I welcome you all in this course on steam and gas power systems, and today we will start with the review of thermodynamics. The topic to be covered in this course are basic terms in thermodynamics, thermodynamic processes, laws of thermodynamics. Now, there are certain basic terms in the thermodynamics which we are supposed to understand before we start with this course. The first is system. In thermodynamics, a prescribed region of space or finite quantity of matter surrounded by an envelope called the boundary, that is boundary, and the system is, there are three types of systems. One is closed system, second is open system, and third one is isolated system. So, system is prescribed region of the space. It can be a physical entity or it can be an imaginary volume in the space on which the thermodynamic studies are concentrated. In closed system, for example, this room can be considered as a closed system. If we seal all the doors and windows of this room, then in this room heat transmission can take place through the ceiling or the wall or the floor of the room, but mass transfer cannot take place. So, in a closed system, mass transfer is not possible, but heat transfer is possible. Now, second type of system is open system. In open system, mass transfer and heat transfer both are allowed. For example, if I open the doors and the window of this room, then air can come into the room and air can leave the room also, and heat transmission through the walls and the ceiling and the floor of room can take place. Then this room becomes an open system. Now, third type of system is isolated system. Isolated system means there is no mass transfer and there is no heat transfer. That is possible if I insulate all walls of this room and floor of this room, close all the windows. In that case, there will not be any heat transmission from the surroundings and the room will become an isolated entity. Now, surroundings. Anything outside the system is surrounding. So, anything, entire universe outside this room is surrounding, and system and surrounding together, they make universe. Now, state, unique condition of the system at an instant of time described by its properties. So, state of a system can be described by the properties, and minimum two properties are required to describe a system, okay. And so, a state can be defined with the help of two properties. Now, process. Suppose system is moving from state 1 to state 2, right, and moving from state 1 to state 2, it passes through a number of states. Now, combination of this number of states together will form a process. Let us say process 1 to 2. Now, cycle. A cycle, thermodynamic cycle can be defined as, there is a combination of, a cycle is a combination of thermodynamic processes. Let us say from state 1 to state 2, state 2 to state 3, state 3 to state 4, state 4 to state 5, and state 5 to state 1. So, final state of the last process and initial state of the first process, if they are same, then this is called a thermodynamic cycle. In thermodynamics, there are two things, heat and work. The entire the philosophy of the thermodynamics is based on the interaction between heat and work. So, in thermodynamics, there are two types of work. One is boundary work, another is shaft work or flow work. Now, in boundary work, the work is done by the movement of the boundary. Suppose there is a system. If there is a movement in the boundary of the system, work will be supposed to be done by the system. An example is given there. There is a piston cylinder arrangement, and inside this red line, this is the system. Now, if we are giving heat from the bottom, while giving heat of the bottom, this gas inside this piston cylinder arrangement will expand. The weight is constant, the pressure is remaining constant. Due to expansion of the gas, the volume of this system will increase, and work will be is supposed to be done. And in this case, in the boundary work, the work is expressed by PdV from state 1 to state 2. Another type of work is shaft work. In shaft work, there is no movement of the boundary of the system. Boundary of the system are fixed, for example, air compressor. So, the physical boundary of the air compressor is fixed, but if you measure pressure at the inlet and outlet, you will find in a compressor outlet pressure is higher than the inlet pressure, and work is done on the gas to increase the pressure. Vice versa in case of turbines. In the turbines, the expansion of gas takes place, and due to expansion of the gas, the pressure drop is there, and due to this pressure drop, we get shaft work from the gas turbines, and this shaft work is expressed by minus V dP from state 1 to state 2, where V is the specific volume and dP is pressure drop. Now, after this we will discuss the laws of thermodynamics. There are 4 laws of thermodynamics: zeroth law, first law, second law and third law of thermodynamics. Zeroth law is the youngest law. Now, zeroth law is the most basic law of thermodynamics, which gives the concept of temperature. Now, this law states if two thermodynamic systems are each in equilibrium with a third, then they are in thermal equilibrium with each other. It means if there are 3 bodies, suppose A, B and C. Now, A and B is they are in thermal equilibrium. It means there is no heat transmission between A and B, either from A to B or B to A. Now, B and C are also in thermal equilibrium. It means there is no heat transmission from B to C or from C to B. So, definitely this A and C shall also be in thermal equilibrium. This is stated by the zeroth law of thermodynamics, and this law gives the concept of temperature in thermodynamic systems. Now, the first law of thermodynamics. The first law of thermodynamics states that in a cyclic process, net heat given to the system is net work done by the system. First law of thermodynamics does not speak anything about the internal energy. The concept of internal energy is derivative of the first law of thermodynamics. So, in a cyclic process, as I mentioned earlier, cyclic process is a combination of processes where, let us say 1, 2, 3, 4. So, 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So, it is a combination of the processes where initial state of the first process is the final state of the last process. So, in a cyclic process, cyclic integral of heat given to the system is equal to cyclic integral work by the system, right. Now, let us take a cyclic process A to B. This is A, 1 to 2. So, from 1 to 2 I am going through path A and coming back by path B. So, according to this, integral from 1 to 2 delta q plus integral from 2 to 1 delta q b, and this is q a, is equal to integral of work 1 to 2 delta w a plus integral from 2 to 1 delta w b. So, here we have taken cyclic integral of heat interaction and cyclic integral of work interaction. Heat transfer in process 1 to 2 and heat transfer in process 2 to 1, work done in process 1 to 2 and work done in process 2 to 1. Now, instead of coming by B, if I come to state 1 by C, path C. Now, in this case again we will use this equation 1 to 2 delta Q A plus 2 to 1 delta Q B is equal to 1 to 2 delta W A, sorry, now this is not B, this is C, 2 to 1 delta W C. Okay. Now I subtract this equation from this equation. So minus 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 QA will be cancelled out, right, and 2 to 1 delta QB minus 2 to 1 delta QC is equal to, and this also will also be cancelled out. So 2 to 1 delta WA plus, sorry, this is minus 2 to 1 delta WC, right. So we have subtracted this equation from this one, and finally we are getting this equation. Now this is WB, not WC, this is WB, right. Now we rearrange these terms and we will get integral 2 to 1 delta QB minus integral 2 to 1 delta WB is equal to integral 2 to 1 delta QC minus integral of 2 to 1 delta WC. Now delta Q minus delta W from 2 to 1 by path C B is equal to delta Q minus delta W from 2 to 1 via path C, or we can write like this, del QB minus del WB by path B is equal to del QC minus del WC by path C, right. Now we can choose another path D, we can come back from 2 to 1 by D as well. In that case we will get another term delta Q minus delta W D. So it means we choose any path, this difference is going to remain constant. If we are coming from state 2 to state 1, irrespective of the path chosen, we can take this path also E, irrespective of the path taken, we will be getting a constant. Now this constant is W is constant, because this delta, this is also energy, this is also energy. So this constant has to be a term of energy, and it is expressed by E. Now E involves everything: kinetic energy, potential energy plus internal energy. But in a closed system the change in the kinetic energy or internal, this is delta T, this is dt, this is dt, dE. Change in potential energy is negligible. So a new term has come into the picture, that is del Q minus del W is equal to du, and du is change in the internal energy of the system, and this is a derivative of the first law of thermodynamics. However, the law remains same. In a cyclic process, net heat given to the system is equal to the net work done by the system. Now after the first law we can take up the thermodynamic processes, then we will take the second law. There are certain thermodynamic processes, standard thermodynamic processes. Now first is isothermal process. Isothermal process, as it is clear from the name itself, if we take on PV diagram, pressure volume diagram, isothermal process will be depicted by a curve like this. In isothermal process, the temperature remains constant and the product of pressure and volume is a constant. So at a constant temperature T1, from state 1 to state 2, an isothermal process will follow a line like this. If I change the temperature, suppose I change the temperature to T2, another curve parallel to this curve will be formed, but these two curves will never cut each other because they are parallel to each other. So, this is temperature T2 and temperature T2 is greater than temperature T1. Now, another process is isobaric process. In isobaric process, as it is clear from the name itself, the pressure is constant. So, the pressure is constant means if you are going from state 1 to state 2, then pressure will remain constant. This is known as isobaric process. Another process is isochoric process. In isochoric process, if I depict this process on pressure and volume diagram, then it is a constant volume process from state 1 to state 2. Now, the next process is polytropic process. In polytropic process, PV raised to power n is equal to constant. So, if I want to show polytropic process, expansion process, it is going to be like this 1, 2, 3. Another process is adiabatic process. In adiabatic process, there is no heat interaction with the surroundings. So, such type of processes are known as adiabatic processes. And another is isentropic process. In isentropic process, the entropy remains constant. So, a reversible adiabatic process is known as isentropic process, and then it is like this: PV raised to power gamma is equal to constant, where gamma is the ratio of specific heat at constant pressure and specific heat at constant volume of the gas. Adiabatic process can be isentropic process if it is reversible. But in adiabatic process, there is a condition that there should not be any heat interaction with the surroundings, but entropy generation due to internal resistance of the system can take place, right. So, that is why a reversible adiabatic process can only be the isentropic process where change in entropy is 0. Now, first law of open system, because this first law for open system is very much relevant to this course on steam and gas power. Now, first law for open system states that heat interaction, work interaction is equal to change in enthalpy. Now, enthalpy has come into the picture, C dC, change in kinetic energy and change in potential energy. Now, this enthalpy H of any gas is internal energy plus PV, pressure and product of pressure and volume. This product of pressure and volume is also known as flow energy. So, internal energy, if you have to find internal energy of the gas, then it is H minus PV. So, we will be frequently using these relations in the subsequent lectures, and there we will discuss the application of the first law of thermodynamics for open system in case of turbine, compressor, nozzles and heat exchangers. After this, we will take up the second law of thermodynamics. The second law of thermodynamics has a lot of relevance, because this law states in a nutshell that if we draw certain amount of heat from a reservoir, the equivalent amount of work cannot be produced. It means there is a thermal reservoir. Thermal reservoir means a body which has very high thermal capacity, right. Thermal capacity means the product of M and C, mass and specific heat, or we can say a body which is having a very high thermal capacity, or we can say that you draw any amount of heat from this, the temperature of this body will not change, because Q is equal to mc delta T. So, if this is tending to infinity, mc, then definitely this delta T will be tending to 0 for a certain amount of heat drawn from the thermal reservoir. So, from a thermal reservoir, if you draw certain amount of heat, you cannot do certain amount of the equivalent amount of work cannot be done. Now, it has two statements. Kelvin-Planck statement and Clausius statement. Now, the Kelvin-Planck statement says that it is impossible to construct a device that will operate in a cycle and produce no effect other than the rising of weight and the exchange of heat with a single result. That is what I have said earlier. So, this type of device is not possible, which work on a cycle, which operates on a cycle, and net effect is the transmission of conversion of heat which is drawn from the reservoir in equivalent amount of work. There is another statement also for the second law of thermodynamics, and it says that heat by its own cannot flow from lower temperature to higher temperature. Now, the exact statement of the Clausius statement is like this: it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a cooler body to a hotter body, right. So, both statements are not different, they are same, and violation of one statement will automatically lead the violation of another statement. Now, we can first of all we can assume there is a violation of this Clausius statement. Now, if there is a violation of Clausius statement, then heat by its own can flow from lower temperature reservoir or lower temperature body to a higher temperature body. So, certain amount of heat can by itself can flow from lower temperature to higher temperature. QL, this is QL, and there is a heat exchange, there is a heat engine which is drawing certain amount of heat from high temperature body and rejecting QL to the lower temperature body, and net work done by this heat engine which is working on a cycle will be QH minus QL, right, as shown in the slide also. Now, if we club these two slides, these two devices, now it is something like QH minus QL is drawn from here, an equivalent amount of work is being done because QL is heat is rejected here and the same amount of heat is drawn from the lower temperature reservoir. So, this can be eliminated. Now, again violation of the Planck statement will lead to the violation of Clausius statement. Suppose we are able to make one device which sole effect is to draw a certain amount of heat from high temperature reservoir, that is QH, and do equal amount of work, W is equal to QH, and QL is going to be in that case 0, or this thermodynamic device has 100% efficiency. Now, in this case, suppose I want to draw a certain amount of heat from lower temperature reservoir, that is TL, and this QH will be used to pump this heat to the high temperature reservoir, that is Q plus QH. Now, if I club these two devices, right, now in this case what is happening, we are taking QH amount of heat and it is transmitted from lower temperature and it is being transmitted to higher temperature, this Q amount of heat from lower temperature, and it is being transmitted to higher temperature without any external work, because QH which is going here, it is moving in this loop only, right. So, this is automatically violation of Clausius statement. So, both statements are same, and the conclusion of the both statement is that we cannot have a device which is working on thermodynamic cycle, and sole effect is the conversion of heat from the sole effect is withdrawal of heat from a reservoir and do equivalent amount of work, and according to the Clausius statement, a device is not possible which sole effect is to transmission of heat from lower temperature to higher temperature without any external work. Now, we will discuss the difference between gases and the vapors. Now, if you draw a PV diagram, pressure and volume, and this is x is equal to 0, x is equal to 1. The constant, this is temperature line, constant temperature line is almost vertical, it is not vertical, then horizontal, and then it takes another curve shape, state 1, 2, 3 and 4, state 4. Now we keep on increasing the pressure. When we keep on increasing the pressure, this constant temperature line will also keep on shifting. And at the critical temperature, the curve becomes almost horizontal, and then we get curve like this. We move far away from the critical temperature, the curve has this nature, and when the temperature is greater than 2 times the critical temperature, it follows the law PV raised to power C, that is product of pressure and volume is constant, as in the case of gas. So, vapor can be considered as a gas when critical temperature is 2 times greater than 2 times the critical temperature. For example, for water, the critical temperature is 373.95 degrees centigrade. Critical temperature of water is 373.95 degrees centigrade, and you convert this into Kelvin, it becomes 647.1 Kelvin, right. Now, water can be considered as a gas when the temperature is 2 times of this absolute temperature, and it turns out to be 1021.05 degrees centigrade. So, at this temperature of steam, the steam can be considered as a gas. That is why we have steam tables, because steam does not follow the law, ideal gas law, PV is equal to RT, because this law is for ideal gas. So, beyond this temperature, steam can also be, we can derive the properties of steam using this equation. Now, if the pressure is very low, for this temperature it is irrespective of the pressure, but if the pressure is very low, let us say pressure is less than 10 kilopascal, in that case, irrespective of the temperature, the vapor will be considered as a gas. That is why in air conditioning analysis, or in refrigeration and air conditioning, when we take air consists of water also. So, water vapor present in the air is considered as a gas, because partial pressure of water vapor in the air is less than 10 kilopascal. However, in the case of steam power plants, when the steam is at a pressure of 40 bar or 50 bar, it is not considered as a gas. That is why we need a steam table in order to find the properties of the steam. So, that is the end for this lecture on review of thermodynamics. In the next class, we will take the Rankine cycle. Thank you.